Come on, my dears, read the statement of illustration number 4. Have you read it? Look here now. Look constantly on the board. Here we have time varying magnetic field in vertically upward direction. Correct? Why it is time varying magnetic field? Because formula of B they have given as B0 plus alpha into T. B equals to B0 plus alpha into T. But B0 and alpha they are constants, but as time will change, come on, the whole value will change. That is, magnitude of magnetic field is going to change with time. That is why I am saying time varying magnetic field. Fine. Now, in that time varying magnetic field, we have one circular loop with radius small r. Fine. Now we are asked to find out electric field on the rim of that ring. That is, on the circumference of that ring, we have to find out electric field. Let us find out. First of all, recall Faraday's law on electromagnetic induction, and it was E equals to minus d phi by dt. That is minus d by dt of phi. And you know, whenever planar loop is perpendicular to magnetic field, at that time formula of phi is phi equals to AB. Fine. Now minus d by dt as it is. What about A? That is area of a given loop. Given loop is circular having radius small r. So naturally area will be pi r square. What about formula of B? They have given in the statement E equals to B equals to B0 plus alpha D. B equals to B0 plus alpha D. Come on. Because pi r square term is constant, I can take it out of the symbol of derivative. And now in this bracket, we are supposed to take the derivative of each term one by one. Come on, derivative of this constant term is 0. Alpha is constant. D by dt of t, it is 1. Fine. And now alpha into 1, that is alpha. Alpha plus 0, that is alpha. Minus pi alpha r square. Minus pi alpha r square. Now if you take magnitude, then mod of E will be, from minus it will become plus pi alpha r square. Mod of E is pi alpha r square. Fine. Now remember, definition of EMF is also given this way. It is nothing but work done per unit charge. Work done per unit charge. So mathematically we can write total work done divided by total charge. Fine. Now suppose given charge is circulated on the rim of this ring and is brought back to the same initial position. That is how we are just displacing that charge on the circumference and we are finishing one circulation. During that, come on, amount of work done you have studied in first semester. Amount of work done can always be written this way: integration vector F dot vector dl. Work done is nothing but dot product between force and displacement. But because we are undergoing the movement along the closed path, that is why I just put here symbol of closed integration. This empty circle indicates closed integration. Fine. Upon Q as it is. And now tell me, don't you know, force exerted on a unit charge, electric force exerted on a unit charge is nothing but electric field. Let it be shown by symbol capital E. So instead of vector F upon Q, I should write vector E. Instead of vector F upon Q, I am writing capital E. Fine. Now vector F upon Q is replaced by vector E dot vector dl as it is, capital E on left hand side as it is. My dears, be careful. This capital E is capital letter from third ABCD and this is from first ABCD. This indicates induced EMF. This indicates electric field. Be careful for writing the symbols. Both the physical quantities are different. Fine. This capital E as it is, close integration as it is. You know vector A dot vector B, it is by definition A B cos theta. Similarly here vector E dot vector dl will be E dl cos theta. Why theta is taken 0 degree? Not explained in the textbook. Just look here in the figure. Why angle between these two is 0 degree? Look here. See, when this ring is lying in a time varying magnetic field, you know we are going to get some induced EMF. During the production of that induced EMF, you know what happens? If you consider extremely small element of length on the circumference of the ring, actually what happens? That one point loses electrons, another point gains electrons. So if this point is losing electrons, then it will become positive. This point is gaining electrons, so it will become negative. And now tell me, where is the electric field? Direction of electric field is always from positive to negative. From positive to this negative, I have shown direction of vector E, that is electric field. And now, so far direction of displacement is concerned, it is always shown in the direction of a tangent. So if you show direction of vector dl here, it is in the direction of tangent. And in the figure you can see both the vectors, vector E and vector dl, at each point on the circumference of the ring, they point in the same direction. Because these two vectors are pointing in the same direction, naturally angle between them will be 0 degree. That is why angle is 0 degree, because vector is very much parallel to vector dl. Fine. Now, so far magnitude of electric field is concerned, at each point on the circumference of this ring, we are going to get same magnitude of electric field. That is why I have taken it out, because it is constant. Then closed integration dl, because cos 0 is 1. Now this capital E as it is. What about closed integration dl? What does it indicate? It gives you summation of lengths of all the length elements chosen over the circumference of the ring. And that sort of summation will give you length of circumference. Don't you know length of circumference? For a ring of radius r, what is circumference formula? 2 pi r. Fine. What about capital E now? Its formula you know. The magnitude of induced EMF we know it is pi alpha r square. So just place it here, pi alpha square. Come on, I am placing the value of E, pi alpha r square. Here capital E into 2 pi r as it is. Capital E into 2 pi r. Come on, pi ones are pi, r ones are r. And now find out capital E. It will be alpha r upon 2. Alpha r upon 2. Now here alpha is constant, r is also constant. So naturally this term is constant. Mind well, every time you cannot expect this electric field to be constant. Why it is constant here? There is a specific reason for that. Here, no doubt, magnetic field is time varying, but it is varying with respect to time linearly. And because of linear variation, this electric field comes out to be constant. How you can say that magnetic field is varying with time linearly? I am showing you. Look, equation of B, they have given B equals to B0 plus alpha t. Just rewrite it this way, alpha t plus B0. Fine. B equals to alpha t plus B0. Suppose we are plotting a graph of B versus T. At that time, we should take this B on y-axis. So I am just writing y coordinate for that. If I am taking this time on x-axis, I just write x coordinate for it. And this I just match with M, this I match with C. So this equation is very much like equation of a straight line, y is equal to mx plus c. Don't you know this is the equation of a straight line having slope m and having intercept on y-axis equal to c. So this is very much like equation of a straight line. That's why we say relationship of B and T is linear. Because magnetic field is changing linearly with time, then only this electric field comes out to be constant. If magnetic field is not changing linearly with time, then electric field will not be constant. Okay? Read next. Look, here we are given one vector field, and in that vector field, just we are asked to find out whether the given vector field is just indicating magnetic field or not. We have to check whether given vector field is magnetic field or not. Just recall Gauss law for magnetism, which you studied in semester number 3. The mathematical form was this. Look here. Closed integration of vector B over a given closed surface should come out to be 0. Closed surface integration of magnetic field is equal to 0. This is Gauss law for magnetism. So if given vector field is also magnetic field, then for that field also we should get closed surface integration to be 0. Let us check whether really we are getting 0 or not. Now tell me, which vector field they have given? Vector field which they have given is vector capital A equals to x I hat plus y j hat plus z k hat. That is what they have given. Okay. Now in that vector field, what we do, we just imagine a closed surface, spherical surface, closed spherical surface of radius capital R and having center exactly superposing on the origin of Cartesian coordinate system. Say this is x-axis, this one is y, this one is z-axis, and here it is common origin. This much is the radius, which is capital R. Now do one thing, you just select one point on the surface of this spherical part, and that point chosen is P. For this point, its 3 coordinates are x, y, z. X, y, z. Now, with respect to origin, the position vector of this very point is vector capital R. Vector capital R. And you know formula of position vector, which you studied in first semester, x I hat plus y j hat plus z k hat. Here it is. Position vector is x I hat plus y j hat plus z k hat. Fine. And now what I do, I just select one area element, one surface element having very small area around point P. Come on. For that surface element, if you draw surface area vector, then that area vector is this, vector dA. You know area vector is chosen always perpendicular to area, but for a closed surface it is always shown outward, perpendicularly outward. So this area vector at this very point I have shown common perpendicularly outward. Fine. These both the vectors right now they are in same direction, and come on, in the same direction I have chosen one unit vector. That unit vector is small r hat. Fine. Now tell me, let us find out such a term for given vector field. That is why instead of vector B I am writing given vector field, that is vector capital A, closed integration of given vector field over this spherical surface. How much it is? Let us find out. Come on. This closed integration as it is, vector A, given vector field is, they have given x I hat plus y j hat plus z k hat. Dot. Don't forget to put this dot. And don't you know vector is always equal to magnitude multiplied by unit vector. Magnitude of this is dA, and unit vector in the direction of this or this, it is come on r hat. Vector equals to magnitude multiplied by unit vector. Fine. Now tell me, instead of x I hat plus y j hat plus z k hat, can I write vector r? Yes. So instead of this, I can write vector capital R. Dot dA. And don't you know unit vector? In the direction of any vector, if you want to have unit vector, what you should do? You should divide that vector by its magnitude. So r hat can be replaced by vector capital R upon capital R. Vector upon magnitude will give you unit vector. Fine. R hat dot R hat, sorry, vector R dot vector R. Vector R dot vector R. It is R square. In first semester you have studied vector A dot vector A, it is A square. Vector B dot vector B is B square. Similarly, vector R dot vector R will give you R square. dA upon R. D upon R I am writing as it is. Now one R is getting cancelled. Left is R in the numerator, and because it is constant, I can take it out of the symbol of integration. Then close integration dA. Okay. This capital R as it is. Now close integration dA means what? Summation of areas of all the area elements chosen over the spherical surface. And when you add all the areas of all the area elements chosen over a spherical surface of radius R, don't you know, it will give you total surface area of a sphere of radius R. Surface area of a sphere of radius R, what is it? 4 pi R square. 4 pi R square. That's why I am putting here 4 pi R square. 4 pi R square into R, that is 4 pi R cube. Now can't you see? This term is not 0. 4 pi R cube is not 0. In short, this required term comes out to be non-zero. Comes out to be non-zero. If such a term comes out to be 0, then Gauss law is obeyed. Then given vector field can be treated as magnetic field. But right now, this term is not 0. That is why we can say given vector field is not magnetic field. Okay. Read this statement of sum number 6. Come on, read it. Look here now. First of all, try to understand the given physical situation. We have uniform magnetic field vertically upwards. Fine. And that magnetic field are shown with vertically upward violet colored vectors which indicate uniform magnetic field vector B. Now in that uniform magnetic field, I just take a conducting wheel of radius capital R, which is kept rotating in a plane perpendicular to uniform magnetic field with constant angular speed omega. This wheel, what does it do? It rotates about its geometrical axis, which is perpendicular to its plane and passing through its center. Fine. About this axis, it keeps on rotating with a constant angular speed omega. In this wheel, we have certain metallic straight wires or rods which are known as spoke. S-P-O-K-E. Spoke means that linear rod or wire which is connected between center point and point on the rim of the wheel. Fine. Now such a few spokes are shown in the figure, and those spokes are this. Fine. And each of the spoke has same length, and that length also indicates the radius of the wheel. Let it be capital R. Now tell me, in each of these spoke, which is a metallic wire, there are plenty of free electrons, and along with the motion of the spoke, the electrons inside the spoke also are set into motion. And don't you know, whenever any charged particle moves in a magnetic field, it will experience magnetic force. And so far electron is concerned, don't you know formula of magnetic force exerted on electron? Be careful. It is vector Fm equals to E into vector B cross vector V. Remembered? Because electron is a negatively charged particle. For a positive charge, here you can write small q, but here it will be vector V cross vector B. But right now we are talking about electron which has a negative charge, and for that formula is this, E into vector B cross vector V. Now tell me, in which direction this magnetic force will be exerted on the electron? Let us find out. First of all, do one thing. In this spoke, you just consider extremely small element of length between these 2 points. Okay, fine. This length element is chosen at distance small r from the center. And so far this element is concerned, its own length indicates very small increase in value of r. Let it be dr. So dr gives you extremely small increase in the value of r. That gives you length of chosen length element. Now tell me, when the wheel is rotating this way, if you think of instantaneous velocity of this length element, when it comes here, it will be perpendicularly inside the plane of the figure. Perpendicularly inside the plane of the figure. I am showing you how. Look. For this wheel, you just consider this very position somewhere here. Okay? Then you may think of small r, this much distance which I am showing here. This is small r. And so far, you know, direction of instantaneous velocity is concerned, you know it is always in the direction of a tangent. So tangent drawn to this point at this circle will be in this direction, because wheel is rotating this way. So correct? Now tell me, how to find this direction? It is going perpendicularly inside. Perpendicularly inside. So this is the situation. This is vector B, magnetic field. This is vector V, instantaneous velocity. Come on. This is vector B, this is vector V. Now we want vector B cross vector V. Vector B cross vector V. Let us find out that. Come on. Direction of vector B cross vector V. This is vector B, this is vector V. Think of a plane passing through vector B and vector V. And now think of one right-handed screw which is perpendicular to this plane. Now for this right-handed screw, I am supposed to rotate this screw in a manner, first vector rotates towards second vector. First vector is vector B, second vector is vector V. I should rotate first vector towards second vector this way. And same way I should rotate this right-handed screw. If this screw is rotated this way, then it will advance towards left side this way. Correct? So direction of magnetic force exerted on each electron in this spoke, in this situation, is this way. This way means what? Pointing towards the center. That is why each electron will start displacing from the rim to the center. From the rim to the center. And because this end of the spoke, which is connected with rim, loses electrons, it becomes positive, and another end of the same spoke, which is connected at the center of the wheel, because it gains electrons, it becomes negative. After losing electrons, this end becomes positive. After gaining electrons, this end becomes negative. So you are going to have some potential difference across the two ends of that spoke. That very potential difference itself is known as induced EMF. But how much is that induced EMF? Its formula we have to find out. Let us find out. First of all, you talk about this extremely small element of length. Here also it so happens that electrons are displacing from this point to this point. That is why this point is becoming positive, this point is becoming negative, and we are going to have very small induced EMF across these two ends. And that partial EMF I am just showing by symbol dE. What is the formula for induced EMF in this case? It is motional EMF. What was the formula for motional EMF? Magnitude of motional EMF, BVL. BVL. Last time we had studied, correct? But that BVL, if you speak out in words, then magnetic field into velocity into length. Magnetic field into velocity into length. Come on, magnetic field is B, velocity I am taking V, and so far length of this element is concerned, it is dr. Okay, and because here it is partial length, then here I should write partial EMF or fractional EMF. Let it be dE. Come on, B as it is. Don't you know scalar relationship between linear velocity and angular velocity, which you studied in second semester? Come on, V equals to R omega. V equals to R omega. Fine. Now tell me, dE equals to B into R into omega into dr. Just take integration on both the sides. So integration dE, and because B and omega are constants, I can take it out, and integration R dr. Come on, integration R dr. Now summation of partial EMFs will give you total EMF. Come on, B omega as it is. You know lower limit of integration means what? Smallest value of variable, and upper limit means what? Biggest value of variable. Here you can change the position of this length element, and when you change it, small r will change. That is why we call small r right now as a variable. If you choose this length element exactly at the center, then minimum value of small r at the center will be 0. And if you displace this length element from here to here, and if you bring it here, then maximum value of small r will be equal to capital R. When you place this length element here, then this much is the biggest value of R. R maximum equal to radius of the wheel. I mean to say smallest value of small r is 0 at the center, and at the rim of the wheel its biggest value is equal to capital R. That's why lower limit means smallest value, that is 0, and upper limit means biggest value, that is capital R. Summation of partial EMFs will give you total EMF, B omega as it is. Don't you know integration R dr? What is it? Integration R dr, R square by 2. Come on, from 0 to R, 0 to R. Now B omega as it is, instead of small r I am putting capital R. So it is R square by 2 minus, I should put the lower limit, that is 0. 0 upon 2 will be 0. So now ultimately it is 1 by 2 B omega R square. 1 by 2 B omega R square. What is the final formula? Capital E equals to 1 by 2 B omega R square. My dears, please remember this formula. Sometimes what they may do, they may give you values of all this, and they may ask to find out value of E. In that case, you should put this magnetic field only in Tesla, this angular speed only in radian per second, and this radius only in meter, and then only you will get the value of capital E in volt. Fine. Now here, one more interesting fact you must understand. The way we have talked about this particular spoke, same way you can talk about all the remaining spokes also. For all the spokes, it so happens the end which is connected at the rim loses electrons, and hence it becomes positive, and that end of the same spoke which is connected at the center of the wheel, after gaining electrons it becomes negative. For each spoke you are going to have same magnitude of induced EMF. For each spoke, same magnitude of induced EMF. Then the question arises, what will be resultant EMF between center and the rim of the wheel? Let us find out. You can see all these spokes, when they have this much EMF, you can say they all behave as if they are batteries of this much EMF. Then what we do now, instead of spoke, we just represent them by equivalent batteries. So all these spokes, as many spokes, that many batteries I should show in this figure. Now tell me, the negative terminals of all these batteries are connected here at the center, and let that point be this one, and all the positive terminals are connected at the rim of the wheel, and that common point of connection I have shown here. Come on, all the negative terminals are connected together at this point, all the positive terminals are connected together at this very point. And now what do you see in the figure now? This is nothing but mixed connection of batteries. mixed connection of batteries. In case of mixed connection, what is the resultant EMF? Resultant EMF is just equal to EMF obtained out of one row. But here in one row there is only one battery. In one row there is only one battery. So whatever is the EMF of one battery, same will be resultant EMF out of whole mixed connection. And so far EMF of one battery is concerned, how much it is? 1 by 2 B omega R square. 1 by 2 B omega R square. Okay. This much EMF you are going to get between the center of the wheel and the circumference of the wheel. Got it? Thank you. Come on, my dears, read the statement of sum number 7. Come on, have you read it? Look. First of all, try to understand the physical situation given to us. Here we have one uniform magnetic field perpendicularly inside the plane of the figure, and that is why I have shown symbols of cross. Fine. So we have one magnetic field perpendicularly inside, and in that uniform magnetic field we have placed capital U shaped conducting frame, and the plane of that frame is like this, correct, which is perpendicular to applied uniform magnetic field. And now these two are the parallel sides, okay, and perpendicular distance between them is suppose small l. We have one conducting rod which is set into motion towards right hand side with constant velocity v0. This rod is in physical contact with these two arms. Okay, fine. At time t equal to 0, we have pushed this rod with initial velocity, say v0, and here we find that as this rod moves towards right hand side, it gets slowed down because of Lenz's force exerted on it in a direction opposite to its motion. That's why its motion is being retarded. There is some deceleration produced in its motion. That's why velocity keeps on decreasing. At time t equal to t, suppose velocity has become vt. You can see in the figure, this arrow I have shown shorter than this arrow. This arrow is longer, this arrow is shorter. This velocity is bigger, this velocity is smaller. And we are asked to derive the formula of velocity at the end of t time in terms of initial velocity. How to derive that formula? I am showing you. Come on. You have studied how to obtain motional EMF, and in that theory we had shown that we are going to get some induced EMF across these two ends of this rod. In this case it was E equals to minus BVL. What is V? Velocity. But because we are talking about time t, I am writing here symbol Vt, that is velocity at the end of t time. Fine. And now according to Ohm's law, induced EMF should be equal to induced current into resistance. Fine. E equals to IR. Right hand side as it is. Find out I from here. It will be minus BVTL upon R. Okay? Fine. Now let us talk about Lenz's force. Lenz's force, last time we had studied, and if you want to have magnitude and direction of that Lenz's force in this case, it should be found out using Ampere's law. That Ampere's law is this: vector F equals to I into vector L cross vector B. Fine. And now tell me, what about direction of this vector F? it will be in the direction of vector L cross vector B. Vector L should be taken in the direction of current, and here in this situation this end behaves like a positive end, this end behaves like a negative end, and you know this will send current in the outer part of the circuit in this direction from positive to negative this way, and this current when it flows through the rod it is flowing upwards this way, correct? So this is the direction of vector L in the direction of current, and this is the magnetic field. This is vector L, this is vector B, and I want vector L cross vector B. Come on. First of all, think of a plane passing through vector L and vector B. That plane is this, and perpendicular to that plane we are supposed to consider right-handed screw. And now this screw is to be rotated in a manner, first vector rotates towards second vector. First vector is vector L, second vector is vector B. I should rotate first towards second. So this screw, if I'm going to rotate this way, then if this screw is rotated this way, it will advance towards left side, that is this way, correct? So this is the direction of lens force, and because it is opposite to motion, we call it resistive force. Fine. Now what about magnitude of this force? Magnitude of this force is F. I as it is, magnitude of vector L cross vector B, by definition it is LB sin theta, where theta is angle between vector L and vector B. Angle between vector L and vector B, it is come on 90 degree. Fine. So theta is right now 90 degree. Come on, F equals to ma. Everybody knows force is mass into acceleration. I as it is, L into B also as it is, sin 90 is 1. Now m as it is. What about acceleration? You can say it is nothing but time rate of change of velocity. Time rate of change of velocity. Because you are talking about time t, I am writing here Vt. dVt by dt will give you acceleration. And now formula of I is ready with us. It is minus bvtl upon r. Minus bvtl upon r into lb. Fine. And now just find out dVt upon Vt from this equation. dVt upon Vt. Come on. dVt upon Vt. It will be minus b into b, that is b square. Come on. L into L, that is L square. B square L square. This m will come down and this dt will go up. So I repeat, dVt upon Vt. Here it is. dVt upon Vt. That should be equal to, come on, minus b into b, b square, L into L, L square, minus b square, L square upon mr, minus b square, L square upon mr and into dt. Come on, minus b square, L square upon mr into dt. Fine. And now just take integration on both the sides. When I take integration here, integration 1 upon Vt dVt. Integration 1 upon Vt dVt. Minus b square L square upon mr. This part is constant, taken out. Minus b square L square upon mr taken out. Integration 1 dt. Integration 1 dt. Fine. Because here variable is in terms of velocity, we should specify the limits also in terms of velocity. Come on. Initial velocity was v0. Later on at time t, that velocity became vt. So I am taking integration between these two limits, v0 and vt. And here, come on, initial velocity will be at time t equal to 0. That's why I am putting here time t equal to 0. And this is the velocity at time t. Okay. Here variable is in terms of time, so I should specify the limits also in terms of time. At initial moment, this is initial velocity. At final moment, this is final velocity. Fine. And now integration 1 upon Vt dVt, by formula it is natural log of Vt. Natural log of Vt from V0 to Vt. From V0 to Vt. Minus b square L square upon mr as it is. Integration 1 dt is nothing but t. From 0 to t. From 0 to t. Now natural log of Vt, and that is to be found out between these two limits. So we should write first of all upper limit. Instead of Vt, when you write Vt here, natural log of Vt. After putting minus sign, we should write the lower limit, that is V0. So natural log of V0, fine. Minus B square L square upon Mr as it is. Inside the bracket it will be now T minus 0, that is T. Now if it is log A minus log B, then you are going to write according to rule of logarithm. Log A minus log B is nothing but log of A upon B. Similarly, natural log of Vt minus natural log of V0, it will be natural log of Vt upon V0. Natural log of Vt upon V0. Minus B square L square upon Mr, this part as it is, into T also as it is. And now taking anti-log on both the sides. Taking anti-log on both the sides. Anti-log and log will cancel, giving you Vt upon V0. And when you take anti-log of this part, you are supposed to write this whole part in the power, in the index of E. That base is should be E. Base is E. Remember, if it is anti-log of x, it is e raised to x. Anti-log of y, e raised to y. Anti-log of this, then e raised to this. I repeat, take anti-log on both the sides. Anti-log and log will cancel, giving you Vt upon V0. And anti-log of x, then e raised to x. Anti-log of y, e raised to y. Anti-log of this will be e raised to this. So e raised to minus B square L square upon Mr into T. Fine. Now just find out Vt from here. Take this V0 up. So Vt equals to V0 into e raised to minus B square L square upon Mr into T. Correct? Now, when we print any book, might be textbook, might be reference book, there we have scarcity of the space. So if you are going to write this much long and big term in the numerator, I mean in the power, in the index, then it will occupy a lot of space. So just to save the space, what we have adopted new symbol, we don't write this term this way, we write it this way. V0 into exp of minus B square L square upon Mr into T. Exp means exponent. Remember, exponent of x means e raised to x. Exponent of y, e raised to y. Exponent of this means e raised to this. Same term is present here. E raised to minus B square L square upon Mr into T. V0 as it is, Vt also as it is. Okay, fine. Now this is the final formula of velocity which we required. But now try to understand what does it indicate. I am showing you. Just transfer this term from numerator into the denominator. So this power will become positive. And now you can write it this way. Vt equals to V0 upon e raised to B square L square upon Mr into T. All these factors are constants except time. When time will continuously increase, come on, this whole denominator will increase, this ratio will decrease, so velocity will go on decreasing. As time passes on, velocity goes on decreasing. But how is that decrease in velocity? I am showing you using this graph. This graph indicates that as time passes on, initially velocity decreases quickly, rapidly, very sharply, and then as time passes on, velocity decreases, but with slow rate. So as time passes on, the rate of decrease of velocity goes on decreasing. Rate of decrease of velocity goes on decreasing. Fine. Such a graph indicates exponential decrease in the velocity. Exponential decrease in the velocity. You are not supposed to touch this graph on the time axis, because the moment you will allow this graph to touch on the time axis, then you know on x-axis y coordinate will become 0. So if you allow this graph to touch on time axis, then at that time velocity will become 0. But theoretically this velocity will become 0 only at time t equal to infinity. Infinite time is never going to get lapsed, so it is meaningless to show this graph touching to the time axis. So leave it incompleted like this only. Okay, fine. Now we proceed ahead in the theoretical part. Let us try to understand one short note about self-induction. This is the name of the phenomenon. Which phenomenon is called self-induction? I am showing you. To understand about self-induction, you please consider one conducting coil. Here is that coil. Fine. it has two ends, A and B. Now these two ends are connected with one rheostat, one battery and one key. Fine. And now tell me, in this closed path, if I just put this key, then path is closed, and if battery is there, means if EMF is present, it will send current from positive to negative. So this is the flow of electric current. Okay. Don't you know, current is a source of magnetic field. So if here current is passing through this coil, it will generate its own magnetic field. And the field lines for that magnetic field I have shown in the figure. Then you might have one question, why these field lines are emerging out from this end and why they are entering from this end? Why? What is the reason? Reason we had studied earlier. Can you remember? Look, through this end, if I observe in a direction perpendicular to the cross section of current carrying coil, then this current I will find, look here, this way. This way means what? Anti-clockwise. Say anti-clockwise. And you know, if direction of current is found anti-clockwise, then that particular end will behave like a north pole. That's why I have written here N. Letter capital N indicates north pole. And if this end is north pole, naturally this end will be south pole. Correct? And you know, magnetic field lines will emerge from north pole and will reach the south pole. Fine. Now tell me, from this magnetic field, all the field lines are passing compulsorily through this coil. When all the field lines are passing through the coil, you can say coil will have some magnetic flux. If magnetic flux linked with 1 ton is 5, then for n number of tons it will be n into 5. Now tell me, if I just move the variable terminal of rheostat towards right hand side this way, then what will happen? If resistance will decrease, current will increase. And as this current goes on increasing, it will produce stronger magnetic field, and then this coil will have greater magnetic flux linked with it. That's why I am writing N5 proportional to I. As this current is increasing, the total magnetic flux linked with the coil goes on increasing proportionally. So N5 increases proportionally with the current. Fine. Now remove this sign of proportionality, put some proportionality constant, capital L. This proportionality constant in physics, it is called, look here, self-inductance of coil. Self-inductance of coil, or sometimes we call it coefficient of self-inductance. Coefficient of self-inductance, or simply self-inductance of the coil. Fine. For a given coil, its value is constant. But now let us see on which other factors can it depend. Let us see those factors on which L depends. It depends on 4 factors. Number 1, it depends on number of turns of the coil. It depends on shape of turns of the coil. It also depends on the size of turns of the coil. How much is the size, small or big? Depending upon that, value of L will change. And it also depends on type of core medium. See, right now the medium at the center in the coil may be air medium, may be vacuum, but it has very low permeability. But instead of air or vacuum, if you wind the turns of a coil on a soft iron isolated cylinder, then because of its very high permeability, it has very strong magnetic field inside, then it has very great value of magnetic flux, and because this magnetic flux is more, at that time value of self-inductance is also more. So I tell you that this value of L depends also on the type of core medium. Core medium means the medium present at the center. Okay. Just find out L from this equation. It will be N5 upon I. L equals to N5 upon I. Fine. What is N into small phi? Total magnetic flux linked with a given coil. Let it be shown by symbol capital Phi. L equals to phi upon I. And now, let us define self-inductance using this formula. whenever you find a ratio and you want to define it, the left hand side quantity, what you do on right hand side, you are making this denominator 1 unit. So if you take I equal to 1 unit, then what will be the definition of L? I am showing you very simple. Magnetic flux linked with a given circuit or a given coil per unit current passing through it is called its self-inductance. I repeat, magnetic flux linked with a given circuit or with a given coil per unit current passing through it is called its self-inductance, shown by symbol capital L. Fine. Now, let us see the meaning of self-induced EMF. Okay. Just do one thing. You change the position of this variable terminal of this rheostat. If you slide it towards right hand side, resistance will decrease, current will increase. Just speak reverse. If you slide this terminal, say towards left side, resistance will increase, current will decrease. So if you change the position of this variable terminal continuously, then this current will change continuously. Depending upon value of current, you will have different values of intensity of magnetic field here. I mean to say, when you change this current, the strength of magnetic field will also change. And depending upon that, the magnetic flux passing through this coil will also change. And don't you know, whenever there is a change in magnetic flux, we are going to get some induced EMF across the two ends of the coil. But here, for the change of magnetic flux, no external agency is responsible. This change of magnetic flux is due to its own. That's why we call that EMF as self-induced EMF. See the word. What is the word? Not only induced EMF, you should say self-induced EMF, because for the production of this EMF, the change of magnetic flux has taken place within the circuit. No external agency is responsible for this. Okay, fine. The EMF developed across these two ends is called self-induced EMF, and this phenomenon of production of self-induced EMF is known as self-induction. Fine. Phenomenon is known as self-induction. Fine. What about unit of L? Unit of L from here. Unit of L will be unit of magnetic flux upon unit of current. What is unit of magnetic flux? Weber. What is unit of current? Ampere. So now unit of L will be, look here, Weber upon ampere. But Weber upon ampere in SI unit system is renamed by Henry. Symbol is capital H. Name is Henry. In the memory of scientist Mr. Henry, we have given the symbol capital H for the unit of self-inductance. Okay. Now, in the later article, I'll show you this Henry can be written as volt into second upon ampere. Volt into second upon ampere. Okay. In case of self-induction also, Faraday's law on electromagnetic induction holds good. So let us use that law. E equals to minus d phi by dt. E equals to minus d phi by dt. That is minus d by dt of phi. Find out capital phi from here. When you find out capital phi from here, transfer this. Come on, capital phi will be L into I. Capital phi equals to L into I. Fine. But for a given circuit or for a given coil, this value of L is constant. Take it out. When you take it out, now left is di by dt. Di by dt. E equals to minus L di by dt. Now from this, if you want unit of L, come on, what is this unit of induced EMF? It is volt. Unit of time is second. Unit of current will come down, that is ampere. Come on, unit of L from this equation, volt into second upon ampere. I repeat, volt into second upon ampere. Here it is, volt into second upon ampere. Okay. Now take magnitude on both the sides. If you take it, then minus will become plus, and then find out the value of L. Value of L will be, come on, make it subject of the equation. It will be E E upon di upon dt. This whole di upon dt you can take in the denominator. Okay. L equals to E upon di upon dt. L equals to E upon di upon dt. Now, if you want to have definition of 1 Henry, then let us take this one as 1 ampere upon second and this as 1 volt. If you put these two values here, this is 1 volt, this is 1 ampere upon second, 1 upon 1 will be 1, L equals to 1 Henry. Then how would you define 1 Henry? Very simple. If time rate of change of current passing through a given circuit is 1 ampere per second, and at the same time if magnitude of self-induced EMF developed in that circuit is 1 volt, then self-inductance of that circuit is said to be 1 Henry. I repeat, if time rate of change of current passing through a given circuit is 1 ampere per second, and at the same time magnitude of self-induced EMF developed in that circuit is 1 volt, then self-inductance of that circuit is said to be 1 Henry. Okay. Please read the question carefully in the examination. If they are asking the definition of self-inductance, then you should define from here. And if they are asking the definition of unit of self-inductance, then you should define from here. That is about Henry. Fine. And now, what is called an inductor? What is called an inductor? Inductor is that circuit element which has property of self-inductance. What do you mean by having property of self-inductance? The meaning is that it should be such a component through which whenever you pass current, it should have some magnetic flux. Not only that, whenever you change the value of that current, you should have some self-induced EMF develop across the two ends of that component. Then that component is said to be having property of self-inductance, and then it can be taken as an inductor. The circuit symbol for showing the presence of inductor is this. This is the symbol for showing inductor. You know how to represent resistance. You know how to represent battery. This is the circuit symbol for battery. This is circuit symbol for key. This is circuit symbol for rheostat. Similarly, this is circuit symbol for inductor. Fine. Now, suppose current is passing here, correct, this way. And if that current is increasing with time, then you can take di upon dt as positive. See, if current is increasing with time, di upon dt is positive. Speak reverse. If current is decreasing with time, then di upon dt is negative. Okay. Right now, suppose current is increasing with time, then di upon dt is positive. Fine. Now look, when current will pass, what will happen? When current will pass, what will happen? Surrounding to this inductor, you will have magnetic field. But if that current is increasing with time, then you will have stronger magnetic field produced here, and because of change in magnetic flux, you will have some self-induced EMF develop across the two ends of this inductor. But that self-induced EMF obeys Lenz's law. So it will try to oppose the increase in the current, and to do that, it has to create here positive terminal, here negative terminal, so that you know direction of EMF. It is away from positive terminal this way. This way means opposite to this current. Come on, opposite to this current. So remember, what is the job of inductor? Do you know? Job of resistor is to simply oppose the electric current. But job of inductor is not to oppose the current, but to oppose the change in current. Please note it very carefully. Resistor simply opposes electric current, but inductor does not oppose the current. Inductor opposes change in current. If current wants to increase, it will not allow it to increase. If current wants to decrease, it will not allow it to decrease. It will try to stabilize the current. This is the job of inductor. Inductor increases, inductor opposes both the changes in the current. Might be increase in the current, might be decrease in the current. So mind well, if current passing through the inductor, if it is entering from one end And if that current is increasing with time, then that particular end will become positive. If entering current decreases with time, then this end will become negative. I repeat, if current entering from here is increasing with time, then this end will become positive. If this entering current decreases with time, then this end will become negative. Fine. Then, because this direction of EMF, direction of self-induced EMF is opposite to this flowing current, that's why sometimes we call self-induced EMF as back EMF. Self-induced EMF is also known as back EMF. Now tell me, how much is the magnetostatic potential energy stored in an inductor? First of all, try to understand how magnetostatic potential energy is getting stored in the inductor. How? What is the reason? See, when you pass current through inductor, it will produce its own magnetic field. And in that magnetic field, some energy is stored in the form of what is called magnetostatic potential energy. How can we say that it has energy stored in the magnetic field? How can we say? What is the reason? See, if you bring some bar magnet here, or if you bring some magnetic needle here, then this magnetic field produced in the inductor simply exerts some magnetic force on that bar magnet also, on that magnetic needle also. I mean to say, this magnetic field has got some capacity of doing work. And you know, whenever any body, any system has the capacity of doing work, means it possesses energy. Here this capacity of doing work is due to particular state, particular configuration, then we call it potential energy. But here we are talking about magnetic field, so we have given the name magnetostatic potential energy. Now tell me, what can be the formula of magnetostatic potential energy? I am showing you. Now suppose current is passing from this end and that current is increasing with time. If current is increasing with time, then this end becomes positive. So direction of self-induced EMF is just opposite to this flow of current. Just think, if the EMF, direction of EMF is this, and then also we want to increase the current through this inductor, then we need to spend some energy. We need to do some work. Amount of electrical work done in time dt is suppose dW. Don't you know formula of work done? It is power into time. Power into time. This is amount of electrical work done. Then this is electrical power. Electrical power is nothing but magnitude of self-induced EMF into current into dt. So this power is EMF into current. Fine. Now dW as it is. Find out E into dt. Look, I is as it is. I is as it is. Find out E into dt from here. Take this dt up. Okay. Take this dt up. So you will get E into dt and transfer this di over here. So E into dt will be L into di. E into dt will be L into di. E into dt will be L into di. Fine. And now take integration on both the sides. So here integration dw, because L is constant, taken out. Integration I di. Integration I di. Integration I di. Fine. Now summation of partial amounts of work done will give you total work done. This L as it is. Integration I di is nothing but I square by 2. Fine. Now this W has come out to be 1 by 2 Li square. 1 by 2 Li square. This will give you amount of energy stored in an inductor in the form of magnetic field, in the form of magnetostatic potential energy, which is shown by symbol UB. Remember? Similar formula for electrostatic potential energy stored in capacitor. Then it was U equals to 1 by 2 CV square. U equals to 1 by 2 CV square. Let us obtain some two other equivalent formula for UB. Very simple. Can you rewrite 1 by 2 Li into I? 1 by 2 Li into I. Come on. What is L into I? What is L into I? It is nothing but capital Phi. So here when you write 1 by 2 Li into I, but Li is Phi and into I. Now just put the value of I. Value of I from here will be phi upon L. So if you write here I equals to phi upon L, then phi into phi will be phi square upon L. 1 by 2 phi square upon L. And similar two formula you had studied in third semester in case of capacitor. They were 1 by 2 QV and 1 by 2 Q square upon C. These are the three formula for magnetostatic potential energy. And now UB once again now written here equal to 1 by 2 Li square, U equals to 1 by 2 Cv square. And don't you know kinetic energy formula in mechanics, it is half mv square. If you just compare these electrical quantities with these mechanical quantities, then you will find some similarities, some analogy between different physical quantities. Here this is also energy, this is also energy. But here this is self-inductance, which is analogous to mass in mechanics. Come on, there is a similarity between inductance and mass. Similarly, this current is similar or analogous to velocity. So there is an analogy between current and velocity and between self-inductance and mass. Okay.